Even if you only make the same requests over and over again, you'll get a slightly different response time on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of response time not as a single number, but as a distribution of values that you can measure. Figure 1.4 illustrating mean and percentiles, response time for a sample of 100 requests to a service. So this also relates the tail latency that we will discuss next, because we measure this not just in one spike or the extraordinary or extremes, but on the median or on the average. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive, i.e., because they process more data. But even in a scenario where you'd think all requests should take the same time, you get variation. Random additional latency could be introduced by a context switch to a background process. So because you have a lot of outside factors such as context switch, network packet loss, hardware failure, etc., you'll get a lot of this along your request response. The loss of a network packet and TCP retransmission, a garbage collection pause, a page fault forcing a read from disk, mechanical vibrations in the server rack, or many other causes. Usually, it is better to use percentiles. If you take your list of response times and sort it from fastest to slowest, and the median is the halfway point, so usually you need to find the average out of those, but getting an average is not as simple as dividing that from the total of number of requests. Note that median refers to a single request. If the user makes several requests over the course of a session, or because several resources are included in a single page, the probability that at least one of them is lower than the median is much greater than 50%. So what we mean is that as you increase your request, the probability that it is greater than that at least one of them is lower, or one of them do not get the median or the median expected response time, the greater the probability that it would get to those extreme. Basically, the more the workload or request, the more likely you get these extremes. In order to figure out how bad your outliers are, you can look at higher percentiles. The 95th, 99th, and 99.9th percentiles are common, abbreviated P95, P99, and P999. For example, if the 95th percentile response time is 1.5 seconds, that means 95 out of 100 requests take less than 1.5 seconds, and 5 out of 100 requests take 1.5 seconds or more. This is illustrated in figure 1.4 here. High percentiles of response times, also known as tail latencies, are important because they directly affect user experience of the service. So this is the tail latency that we were talking about. Basically, there is some reason the customer has a lot of data in their account, such as in e-commerce website. So if you encounter a latency on those customer, which technically is the most valuable customer, therefore you will lose a lot of revenue. For example, Amazon describes response time requirements for internal services in terms of the 99.9 percentile. Even though it only affects 1 in 1,000 requests, This is because the customers with the slowest request are often those who have the most data on their accounts because they have made many purchases. That is, they're the most valuable customers. It's important to keep those customers happy by ensuring the website is fast for them. Amazon has also observed that a 100 ms increase in response time reduces sales by 1%. 20 and others report that a 1 second slowdown reduces customer satisfaction metric by 16%. On the other hand, optimizing the 99.9 percentile, the slowest one in 10,000 requests, was deemed too expensive and to not yield enough benefit for Amazon's purposes. So just in anything or just like in a operating system, there's no one fit workload that will leads you to both of this extreme, either optimizing for the 99.9 percentile or not optimizing. It's really depends on your workload, so you also need to find a balance based on your use case. Reducing response times at very high percentiles is difficult because they are easily affected by random events outside of your control, and the benefits are diminishing. For example, percentiles are often used in service level objectives (SLOs) and service level agreements (SLAs), contracts that define the expected performance and availability of a service. These metrics set expectations for clients of the service and allow customers to demand refund if the SLA is not met. Queuing delays often account for a large part of the response time at high percentiles, as a server can only process a small number of things in parallel, limited, for example, by its number of CPU cores. It only takes a small number of slow requests to hold up the processing of subsequent requests, an effect sometimes known as head of line blocking. So a head of line blocking is important because one request could slow down the other that on the same queue. Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Due to this effect, it is important to measure response times on the client side. Now, because of that, you always have to measure it from the client side, or from the client's browser, not just your server. So you may have logs on the server, but the real measurement is from your client side. That's also the reason it's important to check your browser when developing. But I mean, there's also an extreme on that. But just to make a point, what you see on the browser is what you see on the customer side. It's also another reason is it's also the reason why Google on uploading their or trying to upload an app to Google Play Store, they ask you to test it in multiple devices first, so that you know that you won't have any debug, because um, that's the end goal. But there's also a value of unit testing, such as testing it on the server first before pushing it to production, especially for large scale app. But it really depends on your goals, right? Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time. Uh, sorry. When generating load artificially in order to test the scalability of a system, the load generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queues shorter in the test than they would be in reality, which skews the measurement. This is also why it's important to be harsh. Uh, the load is harsh on the onset of the development so that you are prepared in case you encounter these edge cases in the real world. Now, percentiles in practice, high percentiles, high percentiles, no, high percent, yeah, high percentiles become especially important in backend services that are called multiple times as part of serving a single end user request, which by the way how most server works nowadays, because they have to handle concurrent users, such as how OS provides different services or different ephemeral ports to each of services or each connected network process to its, yeah, to its port numbers, etc. Even if you make the calls in parallel, the end user request still needs to wait for the slowest of parallel calls to complete. It takes just one slow call to make the entire end user request slow, as illustrated in figure 1.5. Here, 487 ms. Even if only a small percentage of a backend calls are slow, the chance of getting a slow call increases if an end user request requires multiple backend calls, and so higher proportion of end user requests end up being slow, an effect known as tail latency application. So this is what you call tail latency application. The head of line blocking is for the queue, but the tail latency is for a backend serving concurrent users. So it's not a queue because you're making the calls in parallel. So even if only a small percentage of backend calls are slow, the chance of getting a slow call increases if an end user request requires multiple backend calls. So if those parallel are related, so that's called tail amplification. Ahead of line blocking is for queue. So they kind of have different use case, because one, you have this queue, or it's not working, or it's not requesting in parallel, while this person does tail of tail amplification are working in parallel, but those parallel requests are actually related from the user's perspective. If you want to add response time percentiles to the monitoring dashboards for your services, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep rolling window of response times of request in the last 10 minutes. Every minute, you calculate the median and various percentiles over the values in that window and plant those metrics on a graph. The naive implementation is to keep a list of response times for all requests within the time window and to sort that list every minute. If that is too inefficient for you, there are algorithms that can calculate a good approximation of percentiles at minimal CPU and memory cost, such as forward decay, T-digest, or HDR histogram. So these are, you can think of this as like a library that kind of compress the data, so that's why it allows them a low memory and CPU load for providing these percentiles. So instead of getting it, because on a huge server you'll probably get a lot of a huge volume of requests, therefore it's also expensive in terms of memory and CPU to process that. Beware that averaging percentiles, i.e. to reduce the time resolution or to combine data from several machines, is mathematically meaningless. The right way of aggregating response time data is to add the histograms. So histograms allow us to see it visually, and it allows us to make sense of that large data rather than confusing mathematics full of logs. So figure 1.5, when several backend calls are needed to serve a request, it takes just a single slow backend request to slow down the entire end user request. First, what is tail latency? Tail latency equals slowest responses. For example, P50 equal median, P95 equals slowest 5%, P99 equals slowest 1%, P99.9 slowest 0.1%. So this is kinda how you get the SLA of AWS. They kinda measure it like this. These slow but error cases matter because your users do feel them. How latency relates to timeline reads. Strategy 1. Recall in strategy 1 in Twitter, on read, we fetch tweets from all followed users, merge and then return to the follower's timeline. This requires many back-end calls per timeline read. Example, user follows 1,000 people. Reading timeline requires 1,000 independent reads. I/O call, input or output calls, DB fetches, cache lookups, and merges. So if it doesn't have a cache, of course, it will fetch in the DB. If it's not in the DB memory or in the main memory, it may have to call the disk before it merges us. And this is where the tail latency hits hard. Tail latency amplification. So quote, even if you call backend services in parallel, the end user request waits for the slowest call. This is critical. So how that even a parallel request of the user cause slowness in the user's perspective. This is critical. Example, if each backend call has 1% chance of being slow, P99 latency event, and your request makes 1000 calls, the chance that at least one is slow is 1 minus 0.99 raised to 1000 equal 99.99%. So your timeline read becomes slow almost always. This is why Twitter's early design collapsed. It required many dependent lookups. So because those parallel, even though they are parallel, they are related, you won't return that to the user unless you get everything, kind of like in a queue. A single slow query, the entire timeline read becomes slow, and with millions of users doing this in parallel, disaster. This is exactly tail latency amplification. How this relates to do more work at runtime. So remember Twitter, do more work at runtime. Let's connect it. Fan out on read, strategy 1, which is now being used for only celebrity. Each triggers 100 seconds to 1000 seconds to 1000 backend calls. More calls equal higher chance of hitting a tail event. Tail latency multiplies. Timeline reads become unpredictably slow. Bad UX. Fan out on write, strategy 2. Each read is one chip lookup, i.e. Redis list or memory. Reads have 0 fan out, 0 joins, 0 merges. Only writes fan out, and writes are 100x less frequent. Tail latency becomes irrelevant on reads. This solves the tail latency amplification problem. Key insight: reducing the number of backend calls per request directly reduces tail latency. Strategy 1. Reads equal 1000 calls affected by P99. Tail latency amplified. All reads appear slow. Strategy 2. Reads equal 1 call affected by P99 of a single operation. Tail latency does not amplify. Reads fast and stable. This is why Twitter redesigned timelines. Tail latency wasn't just an annoyance, it was killing read performance at scale. How percentile aggregation relates? The book then explains how to monitor tail latency accurately, keep histograms of response times, avoid naive averaging of percentiles. So the book provides us a caution on using percentiles as a measure. Instead, use tdigest or HDR histogram for rolling windows. for each time. This matter because to detect latency amplification, you must measure percentiles correctly using the right tools or library. If you average percentiles or computed medians only, you'd miss the real danger, P99 events. Your monitoring wouldn't reflect user pain. You wouldn't realize the parallel backend calls amplify latency. So this is actually how you track accurately in your admin dashboard how your users actually is using, kind of like an analytics tool or um, ad tracking tool nowadays. They basically use this in their backend. Twitter system needed high precision percentiles per service and per call histograms, proper aggregation across servers. This guided the move from strategy 1 to strategy 2. How everything ties together. Here's the full picture. First, strategy 1, fan out on read. Heavy DB queries, 1000 calls per read. Tail latency amplified. Unpredictable slow timelines. It broke Twitter early. Strategy 2, fan out on write. Heavy work on write. Read equal O1 chip lookup. No call fan out. No tail latency amplification. Stable. Predictable. Read latency. Scalable to 100 million plus users. Percentile monitoring needed to detect tail amplification, understand real system behavior, avoid false sense of median performance, track P99 and P99.9 specifically, aggregate histogram data correctly. Result: Twitter discovered that read-heavy workloads must avoid fan-out on read because tail latency dominates, amplification makes most requests slow, scaling becomes impossible. Thus, do more work at write time and less work at read time is fundamentally about controlling tail latency. Does tail latency mean 999 requests must wait for one slow one? Yes. For a single user request that triggers multiple backend calls, a one slow request will slow those 999 requests. Example, you load your home timeline. System must fetch tweets from user A, tweets from user B, tweets from user C, up to 1000 followed users. If 999 calls complete fast 2 millisecond, but one call is slow 300 millisecond, P99 latency event. So your entire timeline now loads 300 milliseconds. This is why systems become unpredictable. Users experience random slowdowns. Latency graph looks smooth at P50 but chaotic at P99 and P99.9. So that's why the percentiles did not work, or the latency graph in histogram looks okay at P50 but not okay at P99.9. This is exactly why Twitter abandoned fan out on read. What is tail latency amplification? Tail latency amplification equal the more backend calls a request makes, the higher the probability it encounters a slow one. Mathematically, if each call has a 1% chance of being slow, one request with one call, 1% chance of being slow, one request with 100 calls, 1 minus 0.99 raised to 100 equals 63% chance of being slow. One request with 1000 calls, 1 minus 0.99 raised to 1000 equal 99.99% chance of being slow. Boom! Almost all reads become slow if you scale out. This is exactly why early Twitter broke. So as you can see, the more calls, even one in just, for example, a user timeline with 1000 celebrities they follow, just one request make a 99.99% chance of being slow.